A great pleasure in introducing our speaker today, Professor Joe Labuz. I would note that he was here not that long ago for Professor Dowding's retirement party, where he made remarks of a very different sort than he's going to be making today. So it's an absolute pleasure to have him back to give a technical talk. We're of course deeply disappointed that he's not here in person, but expect we'll be able to do that when the time is right, have him back. And he's been here before, I don't doubt, and will be here again. And that brings me to his educational background. He's from the Chicago region. I didn't actually realize until doing my homework today that he did his bachelor's degree at the Illinois Institute of Technology, and then came to Northwestern University, where he got his master's and PhD. So this is something of a homecoming. And being from Chicago, I do know and remember that from Minnesota that baseball is a particularly fraught subject, and don't ask is the lesson that I learned. He's now not only professor, but head of department at the Civil, Environmental, and Geo Engineering department at the University of Minnesota. He has diverse research interests, including fluid saturated rock, fracture of brittle solids, and development of novel apparatus. He holds many claims to fame in rock mechanics and geomechanics more generally, and he's a fellow of ASCE and ARMA, American Rock Mechanics Association. And then on a personal note, I have to say that he was my professor when I was at Minnesota. I had him for experimental geomechanics, which is where I learned, Joe, among other things, that being skilled at attaching strain gauges requires a bit of neuroses. I remember this vividly from the class. So I think it was in your class that I recognized that being neurotic can be a strength. I've taken that with me ever since. So with that, I'll hand it over to Professor Labuz to present the work that he's going to be covering today, which centers on acoustic emission.
Okay, thanks, Jim. It's an honor to be speaking to the Northwestern group. And I'll be talking about acoustic emission. Certainly, I got my start in acoustic emission, I'm embarrassed to say, at Northwestern and still working on it. So with that, I would like to acknowledge a number of people. The group that I'll be showing results from, Mr. Wang, a visiting PhD student from China, Dr. Assam, a postdoc, and Mr. Hu, a PhD student here. I'm going to start out with a review of some work on acoustic emission, and I'd like to acknowledge a number of former students that have contributed to this work. Early support from NSF and the university is greatly acknowledged. And of course, as Jim said, I am from Northwestern, master's and PhD, and it was an incredible experience, of course, both academically and socially. So I guess at the end of the talk, I'm showing a slide here of a group of mainly students, but there is one faculty member there. So you'll have to guess who that guy is. We can discuss that at the end. Okay, so what is acoustic emission? It's both a technique as well as a mechanism to describe a transient elastic wave that's generated typically by fracture. We'll be speaking about fracture in rock, and I'll be showing results on different types of rock. And the magnitude of the acoustic emission is also then, if I could say, given different names. So within a laboratory setting where the events are of small magnitude, high frequency, it is referred to as AE, acoustic emission. In field-related work, for example, in mining or in monitoring hydraulic fracturing, microseismicity is the term that's often used. So larger events, lower frequency. And of course, and this has been in the popular press lately, induced seismicity. And we'll review some problems related to fluid injection where microseismicity, or greater than micro, small earthquakes have been generated. So basically the scale is just one associated with different magnitudes and then frequencies of the event. And what we're after is recording the time history. So I show a typical time history. Of course, this is related to AE, that is something recorded in the lab. But in terms of not identifying the scale, for example, with time, it could be microseismicity or induced seismicity. Generally, things that we look at are counts, so statistics, locations, XYZ coordinates, as well as an unknown time origin, and the holy grail of AE is the mechanism. So the orientation of the crack, the displacement of the crack, as well as a magnitude, the energy that's released from this particular event. I'll say it now that the analysis will not be able to discern between the two vectors, N and B, that is the normal and the displacement. And we will not be able to separate the magnitude, that is B delta A, where delta A is the new surface created by this event, this crack. So in terms of, as I said, popular press, certainly this induced seismicity from fluid injection, and it's not so much related to hydraulic fracturing, but related to the fluid that's left over from hydraulic fracturing. There are other interventions that we engineer, for example, enhanced geothermal systems where fracture needs to be developed in deep reservoirs, possibly pumping CO2 into the earth could also, if we're not careful, induce seismicity. But certainly most of the issues have been driven by pumping of wastewater. And this is just one example of looking at counts of earthquakes above a certain magnitude that very recently have taken off. And this is in Oklahoma. I guess a number of the students may not know of this, but there was a similar incident in the early 60s, just outside of Denver. The Army was pumping waste fluid within the earth, and a number of earthquakes, induced seismicity was created. This started a large investigation, and in fact did lead to the suggestion that we may be able to control earthquakes by pumping fluid or withdrawing fluid. And a big part of my talk is going to feature locations, and I'm just showing an example from the Rayleigh paper of tracking of slip along a fault that was known to exist, where a number of events were located along this fault. Okay, so I'd like to provide a very brief background on acoustic emission, the theory of acoustic emission. And it's really driven by seismology, the field of the study of earthquakes. I mentioned locations. This problem was solved in the 1900s, and certainly there are a number of different types of techniques that are used to locate the seismic event. In the 1930s, there was a book on seismology that was published. And of course, I wanted to reference a very valuable reference for any work dealing with the propagation of waves, and that is the Akai and Richards textbook on seismology. In the 1940s, the study of microseismics as it relates to the underground, that is a mine, began here in the United States with some very nice work that was being performed at the US Bureau of Mines, which no longer exists. But this report really started the industry, the mining industry, to look at monitoring mines for microseismic activity as an important safety feature. So work really took off then, not only in the US, but South Africa, Germany, Poland, dealing with the use of microseismic as a safety procedure within mines. From a materials viewpoint, or from the laboratory viewpoint, the work really started with PhD thesis of Kaiser, as well as a paper then he published in 1953. And from there, the field of non-destructive testing, of course, work in seismology continued. I reference here things related to rock mechanics, but certainly within the concrete community, the ceramic community, the metals community, there was quite a bit of work that was being done to interpret the signals that were being emitted from processes that, for the most part, are related to fracture. Okay, so with that as the background on AE, I'll focus now, and the rest of the talk will be concerning laboratory experiments, so acoustic emission. I'll review some aspects of lab testing and instrumentation as it pertains at least to the work that's done in my lab. Certain important pieces of equipment that we use. And the focus of most of our work revolves around location. So I would argue that this is the most valuable and maybe the least controversial piece of information that can be obtained from acoustic emission studies. Okay, we have a big advantage in the lab in that we generally know the region of interest in which we want to monitor the deformation processes that are taking place. Typically, that region is on the order of 100 millimeters in size or so. This region, of course, is a volume, so we will sample through the volume. We can position our sensors such that so-called blind spots are not an issue. So this can be important in field studies where, depending upon the sensor array, it may be difficult, impossible, to locate events in certain areas. Because we're working in the laboratory with small magnitude events, the events very small in size, the frequency content is then inversely proportional to the size. So frequency content is on the order of hundreds of kilohertz. So we need a very fast data acquisition system. We sample typically 50 nanoseconds per point. The electronics now are such that we have 16-bit resolution. We simply start recording when the time history exceeds an amplitude threshold. So this is a very simple way of starting the recording process. The digitizers are such that there is a buffer that remembers the information prior to the amplitude threshold. So this so-called pre-trigger region is very important to us in finding the first arrival of the time history. And for our location process, the first arrival of the signal, that is the arrival of the P wave, is what drives the location process. I mentioned that there are 4 unknowns in this location problem. Because of the quadratic nature of the distance equation, we should be working with 5 pieces of information. For example, 5 channels of signals. For us, we use 8. And typically the data is processed after the test. We can look at counts in real time, but in terms of location or other types of processing, it's done later. The key feature of, well, any type of monitoring is the transducer, is the sensor. Because we're looking at very small amplitudes, in fact, the displacements that are measured by these transducers are on the order of 10 to the minus 12 meters. And the typical sensing element is a piezoceramic. So one type of piezoceramic is this PZT. I mentioned the frequency content. Because of this high frequency, typically the sensors are quite small, which has advantages then, of course, in terms of location, considering a point sensor. These signals, because they're very small, are amplified prior to recording, and to reduce the noise, a filter is typically included. So our results for AE are going to be associated with fracture. So I'll be showing results from fracture tests on a beam and bending is our specimen of choice. Of course, we've also looked at other geometries. Because this beam is a positive geometry, that is, once the crack initiates, crack growth is unstable. Unstable in the sense that the force must decrease as the crack propagates. So to achieve a controlled type of crack growth, that is, typically we will be looking at velocities of the crack speed that are not very large. So on the order of 20, 30 microns per second. To achieve that control, we need a closed loop servohydraulic system. The controller becomes very important typically for these types of systems. This controller is this PIDF type of control, where the adjustment of these parameters are done empirically. That is, the tuning is the term that's used for this adjustment, is specimen dependent and something that is very important for testing of brittle materials. The feedback signal that is used must be a monotonically increasing function. For example, I'm showing here now results from a beam test that has a smooth boundary, that is no notch. This is the forced load point displacement response. And you see that the post-peak behavior, which we'll be assuming in terms of analysis that I'll show at the end of the talk, that basically, assuming linear fracture mechanics is valid, that we have a balance in the energy release such that any point within the post-peak response is associated with the stress intensity factor K1 being equal to a material parameter, that is the fracture toughness. And you see the strong snapback response that's occurring with the load point displacement. Whereas the monotonically increasing parameter is the crack opening displacement. So if we measure the crack opening on the bottom fiber of the beam, as the crack initiates, in fact, crack growth is quite rapid in this portion of the beam, because essentially we're going from a crack with this smooth boundary specimen that's on the order of 1 millimeter or 2 for this particular material to something that's on the order of 10 millimeter in length. So this propagation of this fracture is rapid as compared to the propagation that takes place in this softer type of response that we're observing, where control is much easier. I just wanted to mention that the beam is a very nice analog for tensile fracture, certainly within the rock mechanics environment. That is the types of problems where we deal with cavity expansion, for example, in hydraulic fracturing. This is a tensile fracture type of process, indentation mimicking rock cutting, again, a tensile type of process. At least that's what is hopefully achieved in indentation. So as I said, I'll concentrate on the failure mode of tensile fracture in the flexure, in the bending type of loading. And for the most part, the loading configuration will be 3-point bending. We have done cavity expansion, splitting, Brazilian testing, indentation, and of course, confined compression. But I'll be concentrating on the tensile failure results. The location problem, as I said, has been well studied. For us, the problem is not that difficult in the sense that our material is more or less homogeneous. For the most part, we work with rock that's fairly isotropic. So the location problem is not difficult. Because of the amount of data that can be generated, picking the first arrival is usually done through some algorithm. So for example, I'm showing an acoustic event that is a signal that's recorded on 4 channels. And the important information for us, again, related to locations, is this first arrival. So picking this first arrival for thousands of events must be done automatically. We measure P wave and S wave velocity as a way of characterizing the material, but we also, the term we use is calibrate the velocity, because as I said, for most rock, there is some, hopefully only slight anisotropy. And this assumption of isotropy can be smoothed by a procedure where we generate an event at a known location. So of course, an artificial event, we break a capillary. We know that location and we can adjust the wave speed to reduce the error to the smallest possible value. And then we would use that velocity in our location algorithm. We typically do not update the velocity. So depending upon the failure process, this is something that may need some attention. But for tensile fracture problems, because the volume of damage is quite small, I don't see this as a limitation of the analysis. Okay, a nice way to look at locations is graphically, and for a 2-dimensional problem, it's easy to show, it's easy to construct. I should mention something about error, and of course this is in quotes because we don't know the answer. So we calculate a location. From that calculated location, in reference to the position of each sensor, we can calculate a distance. And we can compare that distance that we compute with a distance that we also compute, because we have to find the original time, the time in which that event took place in reference to the arrival of the signal. So this time difference multiplied by the P wave velocity gives us another distance. And this difference for each sensor gives us a measure of, we call it error. So in terms of the 2D analysis, we can construct hyperbola. So this is a parametric equation for a hyperbola. Delta T subscript 1, 2 is simply the relative arrival time between 2 sensors. So again, I'm showing a time history that's recorded from one event on 4 channels. And the red arrow indicating the first arrival of the event associated with the P wave. So channel 1 in reference to channel 2 has a difference in time that we can measure, and that's the delta T that would be used in computing the characteristics of this hyperbola. And of course, we do that for a number of events, and where those cross indicates the location. I should make the comment that this is a very good signal in the sense that if we look at what the nature of the signal is prior to the event coming to arriving at the sensor, this is a very low noise. So the signal to noise ratio here is very good. I could show that this is a little not as good, but still I would say very good. There are signals, and picking out the P wave is quite difficult. The other thing I'll mention is that typically we'll allow the resolution of our measurement to clip the time history. So it may be that the threshold for recording is at this level of amplitude because of the pre-trigger feature of the data acquisition system. We're able to record the time history prior to that threshold. Okay, as I said, we record thousands of events, and the solution then needs to be developed where we have a numerical algorithm. We have 4 unknowns, and we can set up an optimization problem where we minimize an error to find these 4 unknowns. The things that we do know, the arrival times, we take the P wave as a known quantity. It can be treated as an unknown and found within the minimization procedure. I mentioned the automatic picking of the first arrivals. And again, this is set up to be solved in a least squares type of algorithm. I'm now showing results again for a beam test with a smooth boundary, no notch. And these are locations of acoustic emission. I'm showing them just on the XY plane. So I should have indicated a coordinate system. For us, X will be in the horizontal direction, normal to the development of the macro fracture that will appear in this beam. Y is in the vertical direction, and Z is in the thickness direction out of plane. So I'm just showing the XY coordinates of these events prior to peak load up to about 98% of peak load. And I would argue that these events are more or less random, that I cannot readily identify where the crack will start developing. If we now remove these events, and I should say these events are located with an error less than 2 millimeters. So these are good locations. I now remove these events and I show events only in the region right around peak load. So this is a typical load displacement response. I showed this earlier, so it's not for this beam, but the important thing is I'm looking at 98% of peak, before peak, and after. So there is some post-peak response here. And obviously the picture is much different. We have a clustering of events that clearly indicates where the fracture has formed, what I'll call a fracture. The other thing to note is this is a smooth boundary. The loading is 3-point bend. The maximum moment, of course, is along the line of symmetry of the beam. That's the position 0. But the fracture is developing slightly off center because of possibly local heterogeneity of the beam, as well as possibly some imperfections in our loading system. That is how we position the beam. These are, again, the same results. This particular beam was of 75 millimeter height. If we test the same material, similar geometry, but double the height, this beam now is 150 millimeters in height. I would argue that the picture of this clustering of the events, again, around peak load is very similar. So this fracture, at least for this material, for these size beams, is developing in a similar manner. Okay, besides just looking at what happens around peak load, we can use these events to monitor propagation. So now I'm showing results of locations into the post-peak region. So this is post-peak, 85% of peak load to 80%. So of course the load is decreasing because of this controlled fracture that is being followed using this closed loop system. So the crack these locations are indicating a crack that's growing because of course we're prescribing this constant rate of crack opening displacement. So I would argue that AE may be one of the most effective ways of monitoring fracture, including propagation. It has the advantage of sampling the entire volume. A disadvantage is, of course, there's location error. So if we want to determine a crack length of 10 millimeters and we have an error of plus minus 2 millimeters, that may not be of a fine enough resolution. So what to do? Well, in a laboratory setting, we can use optical methods. So we've done that. We started with speckle interferometry, and certainly this is a technique that other people have used. So we copied from work at Northwestern with Professor Shah's group. The nice feature of speckle interferometry is that it's simply based on optics. So the processing of data is trivial. Setting up the optics is quite challenging. So what I'm showing here is a condition that is measured at peak load. And these fringes that develop are due to what I would describe as a displacement discontinuity, a fracture that's forming at the bottom fiber of the beam. And this particular beam is also with no notch, smooth boundary. We can use the information about the fringes because each fringe indicates constant displacement in the X direction only. So it's a limitation of at least our system. And we could track the crack opening profile as well as the position of the tip as this feature is initiating, as the fracture is initiating in the beam. This particular beam is now one where there is a notch present. There are some disadvantages with speckle interferometry. We could not use this within a closed loop system because of the vibrations that come through from the servo valve. So a very convenient technique. Now the optics are trivial. That is, all you need is a digital camera. The processing of the data though is quite intense. In any case, DIC is particle tracking, and we use the data in a way that we plot fringes, that is contours of displacement. So the result in terms of the contours of displacement in the X direction indicate a fracture has formed and propagated quite a bit of distance. We started with a 2 millimeter notch, and we have a crack that has propagated to a position of roughly 18 millimeters in length, as indicated by the merging of the fringes, the contours, and it is well tracked by the acoustic emission locations that accompany these measurements. Okay, so hopefully I convinced you that locations are valuable, is valuable information that can be readily obtained from this technique. I'd like to review with you now theory related to determining more information about the crack, and I'll show you brand new results. So I'm ready for tough questions. dealing with fracture of, I would describe as a brittle rock, a quartzite and a brittle material, so glass. Okay, so the theory in looking at the signals and interpreting these signals as cracks that produced AE is well developed. We'll be following the formulation in a paper that Professor Rice wrote as it relates to non-destructive testing, non-destructive evaluation. So it's well known within elasticity that we could represent a small crack, a dislocation, by force dipoles, by a special combination of force dipoles. Because force dipoles have units of force times distance. In seismology, this combination is referred to as a moment. So the moment tensor for a crack that's opening in the 3 direction with the normal in that same direction has this type of characteristic where lambda and mu are the Lemay constants. B is the opening of that crack, and delta A is the new surface that's created. I should mention that in seismology, generally, earthquakes are associated with shearing type of mechanism. So within seismology, the important part of the moment tensor is associated with this double couple. There often is other parts of the moment tensor that can have a physical interpretation. For example, the other part can represent a crack that opens if the combination of these force dipoles are such that this relationship holds. So to have a crack only model, we need to build our moment tensor to have a certain configuration. Now, another way of approaching this is to look at, instead of the moment tensor, what is sometimes referred to as a displacement discontinuity tensor or a crack tensor. And that's this quantity psi, where B is the displacement vector and N is the normal vector. And immediately you see that we could interchange B and N, and psi does not change. So this is a limitation of the analysis. There is a simple relationship between the moment and the displacement discontinuity, and that's given by the elasticity of the material. So we could write the moment tensor in terms of B, N, and delta A by knowing the elasticity of the material. For an isotropic material, so again, an important assumption for us, the eigenvectors of M and psi coincide. And this is convenient because if we now solve the eigenvalue problem for psi, the displacement discontinuity tensor, we'll be able to write the quantities that we're after. So note that the displacement discontinuity tensor has the intermediate eigenvalue that's 0. Only the major and minor have values, and the magnitude of the event is related to those two. It's the difference. And an important angle for us is given by, again, the minor and major values, eigenvalues of psi. And this angle alpha is a measure of the angle between the first eigenvector and N, or of course B. So this angle will be, the mechanism will only be known if this angle is 0 because then N and B coincide. So the important information that we'll be able to obtain from this analysis will be B delta A, alpha, in which we will be able to compute N and B, but N and B can be interchanged. Okay, so we use an approximation of a point source in an infinite domain. That solution is well known. It's available in various references. So in terms of how we use this solution, we place our sensors at the boundary of a specimen. We claim we can measure, so calibration of the sensors becomes very important. We can measure the displacement at those locations. So we know the displacement, we know the Green's function for this point source in an infinite domain. We need to solve the inverse problem for the moment tensor. The way we need to do that, because we do use the solution that's written out in terms of the moment tensor, we have to guarantee that the intermediate value of M takes this form, because we want the model that's associated with crack only. So we claim we can measure the displacement at the position of the sensors. We calculate the displacement that the moment that is associated with that event would take place, at that position. We do adjust for the free boundary in terms of a mode conversion that takes place at the free surface. And this other part is the constraint that we must impose to get the crack-only model. I'm showing here quickly the results of a calibration experiment where we produce an artificial event, and this artificial event is a rapid unloading that's produced by breaking a glass capillary. So the blue is the signal that's measured. The orange is the, if I could say, signal that is calculated based on the elasticity solution associated with that calibration procedure. And we relate the voltage that we measure from the time history to the to the displacement that's calculated from this elasticity solution. Okay, so let's show some results. The first material is a rock. So we might describe this as a quasi-brittle material, but this is a very strong, stiff, brittle rock. I'll be showing results from two types of specimens: a beam, again in 3-point bending, that has no notch, a smooth boundary, and also a beam with a center notch. The results I'll be showing, although we tested various size beams, so we did perform a size effect analysis to look at conditions associated with linear fracture mechanics size beams. I'll be showing results for a sub-size specimen. So the span is 130 millimeters, the height is 50, the thickness is 30. Of course, a smooth boundary has no initial notch. The other beam that is with the center notch is nominally 10 millimeters in length. This rock is virtually all quartz. The density is quite high, so the specific gravity of quartz is 2.65. We're very close. This material virtually has no pores, only cracks. So the Young's modulus in compression is this value of 70, whereas in tension, it's 55. And if we assume a random distribution of penny-shaped cracks, we would estimate a crack density of 17% based on these parameters, these numbers. The grain size is quite fine. Average size is around 0.3, 0.4 millimeters, and the strength is quite high. So this 340 MPa is on the order of 50,000 PSI. The tensile strength is measured in a beam test with no notch, is also high, is 30 MPa, almost 5,000 PSI. We're using crack opening displacement as the control signal with the feedback signal within the closed loop system. And it's slow. It is 5 microns per second. I'll show you some results where, again, the crack speed is, for us, quite rapid. We were able to control the rate of AE was quite high for us, 90 events per second. And then the crack slows down, this 25 microns per second approximately, with a rate of AE of about 10. This material, this rock, is fairly isotropic for P wave velocity within 2%. This is the P wave. We've calibrated the sensors and just some numbers in terms of events. So the smooth boundary, 3,600, the center notch beam, because we went to a larger crack opening displacement, about twice that number. Locate, we can locate more of them, but this is within a certain error, so 1.5 millimeter error, and we're able to characterize, again, within a certain error, and I'll show you how we define that for these numbers. Again, the geometry, some of the beams, we do have DIC, but I won't be showing those results. So only results related to AE, as well as, of course, mechanical response. Okay, and this is the mechanical response. We're looking at now the smooth boundary is the upper one, and I showed you this result earlier. I don't have the low point displacement, but that is that severe snapback that takes place. Also plotted on this diagram is the Y coordinate of the acoustic emission. So, of course, we have the XYZ coordinates, but this, that's my timer, so I have 5 minutes. This indicates the, I would argue, the growth of the crack, and this is how we measure the crack speed. So this slope, and of course, there should be some nonlinear behavior that is taking place as the crack increases, but it's more or less well fitted by this line, and that gives us a crack velocity of 26, and for the center notch a little faster. And I would say the locations are tracking the fracture. This is the rapid propagation, and this is where we get the 5 millimeters per second of crack velocity. Okay, the alpha values. This is a mode 1 fracture test, and these alpha values are shear dominant. So I didn't say it, but if alpha is equal to 45, that's a shear crack locally, and we have an average value of 41. We also use a polarity method to check against the crack model that we're using, and it gives us similar results. But it's not the complete picture because this is local. So of course the crack has some orientation, and if that orientation is not vertical in terms of how we are setting up our specimen, then just considering that opening is in the X direction, there must be some tangential component. So at least that's how we explain this dominant shear behavior. So these are now the results of the B delta A components by decomposing that vector, of course, this quantity that we give the vector quantity to, the B, in the X, Y, and Z direction. So this is the global coordinate system where X is normal to the fracture that's developing in this rock. And you see the dominance, as you would expect, for the analysis of these crack events. It is interesting to see not only a Y component, but a Z component that is taking place out of plane, right? Certainly these values on the order of 2 × 10⁻³ are much smaller than the BX component, that is the opening. And it's consistent for both beams. And in fact, you see a larger opening just because we have more events for the center notch beam. Okay, let's get to the good part, and that's the glass. Okay, so this is silica glass. It's a polymorph of quartz, so it has a lower density. The elastic properties, Lemay constants that are computed from E and nu, P wave and S wave that are computed from E and nu. We slow down the experiments because it's very difficult to perform experiments on glass, on notch specimens, and control crack propagation. And in fact, we're only briefly successful. And this is specimen 3, so you know that specimen 1 and 2, we were not successful. Geometry is similar to what I showed for the rock. Both specimens that I'll be showing do have notches. One is a deep notch, and that's the successful one that I'll show first. And then this other one, I'll describe a pre-crack. Of course, we calibrate sensors, both in terms of source characterization and for locations. And this is the P wave velocity. This is specimen 9, so it's not the deep notch, but it's the 15mm and 15mm height of the glass beam. This clip is for load point displacement. These are the results. So you see the stress, nominal stress or force, COD. We're only able to control a short period of time in the post-peak region, but we were able to record 15 events. This is a portion of the force load point displacement. The blue is loading, peak load takes place, and you see the severe snapback as we are controlling with increasing COD. This is the command signal, so I'm showing you the COD with time. It should be increasing linearly. The blue dots are the actual measurements. So the difference between the feedback signal and that blue dot is the DC error. And the system wants to minimize that DC error. And you'll see at the end, that is when it was not controlled, the DC error is decreasing, is increasing. This is a blow up around peak load, and the red crosses are associated with, red X's are associated with where we recorded the events. Okay, locations are beautiful. So right around the notch, and this is the deep notch. So this is the 30mm notch in the 50mm beam. This is a blow up of those locations, and this is a tracking of those locations. The locations are well tracked by the yellow or orange line is what would be predicted from linear fracture mechanics. So, okay, we're not doing well here, but this is a small scale off by maybe 1 millimeter. And this indicates the location error. So, okay, this one has slightly larger error, 1.7. Okay, now maybe the surprising result. Let's look at the alpha values. The alpha values are indicating mixed mode. So around 30 degrees. And what I'm plotting now is we're picking N and B. So of course I could switch these, but when we pick the particular N, you see a crack. And what I'm showing here, this is the XY plane. So it's just looking at the components of N and Y on the, NX and YX on this plane. but we're not plotting the normals. We're plotting what I would call a dip vector. So this is a representation of the plane itself, not the normal. So this is the little crack, and this is the opening that has taken place with some tangential component in this plane, right? This is event 8, again, mainly opening, but there is some Y displacement. Event 11, and the arrow does indicate the magnitude. So the magnitude indicated by this, and we're just writing this in terms of B, but there is a delta A there, so we can't take out the delta A. B delta A is a measure of the magnitude. We can compute what's called a scalar moment, and then compute also then the moment magnitude. And then this last event. It's interesting to look at the Z component. So now we'll look down on the beam. So this is in the XZ plane. So again, the opening that we like to see, but there is a significant component out of plane, and that's shown by these numbers, right? These two are going in the opposite direction, but then you see these other two that are in the same direction of Z. Okay, finally, because I'm out of time, it's difficult to control, as that test indicated. So we went to using a sandwich beam. So this was recommended by us, to us by our colleagues in Italy. And this is a very nice paper that was written by a group in Trento. Certainly testing trying to get stable fracture in using stiff elements is not new. Very nice work done at Northwestern. But this is a very simple approach, and it was successful for us. I'm just indicating here what the analysis gives for this type of geometry. And if you choose properly a notch length appropriately, you do have stable fracture that takes place. So we were successful in stable fracture. This is the force displacement response. You see the growth of the crack, see locations of acoustic emission. If we look locally, again, we have mixed mode locally. Globally, the crack, these little cracks are opening with little displacement in the in the Y and Z directions. Finally, we were successful in now with that pre-crack using conventional type of fracture test methods. These are the locations that track the crack. It's interesting to note that there are 2 events that take place within the pre-peak region. So possibly due to some interlocking that has taken place, we do get events along the pre-crack. We were successful in monitoring and controlling crack propagation, similar crack speed that we saw from the test with rock. Again, very strong snapback, and again, mixed mode character, locally opening. Okay, so I'll summarize. I'll just show this slide and stop. So sorry, a little long. Thank you.
Thank you, Professor Labuz. Thanks very much. And if we weren't doing this on Zoom, you would be hearing the applause now. Feel free to, show your reaction on Zoom. And yeah, thank you very much. This is a wealth of information for all of us, and a lesson in how to do careful experiments, I think. I have a couple of questions that I can ask. I'd like to open it up to students, colleagues, anybody else here who, and do you have to run at any moment, or do you have time?
No, I have time. Yeah. So again, I'm sorry. I thought I was doing well on time, and yeah. So,
no problem. I think, John, was that you that had a question?
Yeah, thanks, Joe. That was great. I learned a lot about acoustic emission that I hadn't known before. Yeah, being a theoretician, I have greater appreciation for the difficulties of experiments. I have 2 questions that I think are short. Could the mixed mode behavior be due to slightly deviation of the crack. And then the other question was, as I understand it, you usually only use the arrival of the wave. Is there anything you can do with the rest of the wave train that would be helpful?
Okay, I should have mentioned that. So your first question, Don, I would argue why we're seeing this mixed mode, because locally well, there is some tortuosity certainly within the rock specimens, but it could, and these experiments were just conducted this summer, and we're still analyzing the results, at least for the glass. I mean, I was surprised to see that behavior for the glass, but there could be, because the crack, I mean, strictly speaking, is not simply vertical. So there is some tortuosity. If you get a little crack that is not vertical, there should be, because of the opening in the X direction, there has to be a tangential component. So that's how I would explain why we see that. And your second question is, why don't we use the entire time history? And we did try it. The difficulty with these types of sensors, and I should have said it, is they resonate. So they're incredibly sensitive. So as I said, picometer displacements, but once they're excited, they resonate. So to get useful information, you need to clip the signal, and whether it's worth it, because this complicates the calibration procedure. We think, and others have gone to this route, where we only use the information, as you point out, as the first arrival and that first peak. That's the only information we're using. So that is another limitation of, well, of the calibration procedure.
Yeah, okay, thanks.
Yeah, so you run it, Jim. However,
Yeah.
if there are any other questions that...
Yeah, and we'll, I think we can go ahead, Zdenek. Yeah, go ahead.
Excellent lecture, instructive to me. Can you record acoustic emission?
So sorry, I don't know what happened.
No.
Lost the connection. So
Yeah,
I'm sorry, I didn't hear your question. Something happening to my Zoom.
No, everybody.
I thought you guys cut
lost.
me off because I went too long.
Joe, everybody lost it. So, Zdenek, your mic is off.
Yes, I do reconnect. Yes.
Yeah, there we go.
My question
Zdenek, go
was,
ahead.
we are looking at genesis of cracks in geology, and they generally formed by mode 2. If it's not hydraulic fracturing, as an exception. Do you have any, have you studied mode 2 cracks? They are hard to produce, of course.
Okay. I mentioned that I described it quickly on one slide as confined compression.
Yes.
So, of course, sorry, not of course, but we perform experiments on under some positive value of mean stress in terms of compression positive. And of course, the failure mode that then develops within this element is one of that might be described as a shear band, right? And a
Yes.
fracture that is inclined. And we have used this acoustic emission technique, both for locations, but also in terms of the source, to see the type of events that we would record. And indeed, for that type of loading, these cracks, as we would anticipate, are shear dominant, where again, if we decompose the displacements, they are aligned with the failure plane. So in the sense of the shear crack that develops from this localization problem, we have used the same methods. The difficulty with rock always is rock is always slightly anisotropic. In addition, and I didn't go into that in terms of the calibration for the glass specimens was, I would describe it as very good because we do check how much we call it a sensitivity parameter, changes with position. That is where the crack develops or the artificial event in relation to the sensors. And for the glass specimen, that variation is very small over the distances that we study, whereas for a material such as rock, that is not the case.
Joe, Luca here. I have another question. Following up of John's remarks about the mixed mode feature of the crack, I have two-part comment and the question. Do you think that particularly at the initiation, the shape of the notch might have an effect there? Because the notch is not a sharp notch, of course. It has some shape, and for these materials that are very fine-grained, the glass or even the rock, I imagine that the shape, even if you have a 1 millimeter width in the notch, that the shape of the notch might have an effect in terms of how you initiate the crack at the notch tip. And the second part is, if that is true, then do you see as the fracture propagates that mixed mode to persist or to get reduced? Is there any evidence of that?
Okay, so for your first part, we haven't looked at that. So that's an interesting point. The only thing I would say is, as it relates to the second part, I showed it quickly at the end. We were successful with that pre-crack. And of course, that started from the notch. But now we have a pre-crack. That length was about 4 millimeters. The growth in the pre-crack in terms of the alpha value was, if I recall correctly, was around 26 degrees was alpha. Whereas now, when we fractured that specimen that had the pre-crack, the alpha value was about 30, the average. So we did, and we still need to look closer at this data. So I'm giving you the excuse that it's very new, so it's not published yet.
No, because
we didn't see change in the mechanism, so it's largely the same.
Okay. Because I imagine, if the crack, I don't know, you saw it. If you saw the crack, I mean, if you have the crack made with a saw, and you have a corner, well, the crack might start with the corner, which might not be exactly on the center line. So you definitely are going to have shear there. Yes.
Yeah. Good point. I can say in terms of the rock specimen, the quartzite, there is more, if I could say, more opening in the tip than there is along or behind it. So that makes sense in terms of the tortuosity, interlocking that may take place away from the tip. So that I can tell you, although I didn't show in terms of the detail of the events, because we have hundreds of events there that we've characterized.
Just a brief question. In hydraulic fracturing, do you agree that actual hydraulic fracturing has never caused in the US seismicity higher than 2 on Richter scale?
Yeah, I can't say, Stanek, so I don't know enough about the what actually has been recorded. If that's been reported, I mean, I wouldn't be surprised. The crack velocities are not that large. The material that they're fracturing, for example, they often talk about this shale type material. In fact, you guys have tested it. I mean, it's not, if I could say, a very brittle material, right? It's
very, very brittle. Quasi
brittle, certainly. So I can't really comment about magnitudes of 2 or less, but I wouldn't be surprised. I wouldn't be surprised.
It's a problem, you said that, of course, for injection of waste and that sort of things, which is done from vertical wells usually and often in faulted rock.
Yeah, so certainly, for example, the Rangeley experiment, well, not experiment, but it turned out to be, because they did do other types of injection because they noticed this. Yeah, those events were larger, so 3 or 4. But I think those were associated with activation of a fault. So in terms of,
Okay.
I don't know, the mean stress, the normal stress on that fault being larger, such that, you know, when it reached the conditions, there was a larger release of energy, but it's just speculation on my part. I don't know enough about the details.
Alessandro, did you have a question?
Yes, thank you. Thank you, Joe, for the wonderful presentation and lecture. I have actually only 2 curiosities. One relates to the comment of Gianluca with respect to the influence on the notch on the formation of cracks. So is there any particular technique that you use depending on the stiffness of the material to generate the notch, or it's,
No, so
let's say, the convention?
typically for us, the notch is saw cut. So we use a diamond blade to cut the specimens, and that's when, well,
So
usually a smaller blade, a thinner diameter, a thinner thickness of the blade. So the notch radius, I didn't say it, is 0.5 millimeters. So the blade is of thickness of 1 millimeter, and it's roughly a radius that is developed.
okay.
I don't think I have to look closer, but I don't think we see a difference, for example, in the specimen with the smooth boundary. So if we look once, you know, the propagation takes place, we don't see a difference in the mechanism. So again, locally shear dominant, but we don't see anything different with the notch there or not there.
Okay. Okay. Thank you. And then the second curiosity I have is that, so you mentioned that as a matter of fact, there are these algorithms to interpret the waves and find the beginning. And as you recall, like from some of my previous works, measuring with AE the formation of ice lenses in frozen rocks, that it was a nightmare to find the onset of those peaks. So is there, like, have we advanced on that, like on how to select those times or not?
There's quite a bit of work you could find in the literature on different techniques, different signal processing techniques to find the first arrival. I should have mentioned, and of course, all the credit goes to my students, all this analysis software that I talked about is developed in-house. So these are codes that are written by some phenomenal students. We have looked at different types of techniques to find the first arrival. For us, the one that works the best is simply related to looking at the characteristics of the noise. And when I say characteristics, it's the average value and the standard deviation associated with that average value. So we take an absolute value of the maximum amplitude for the noise. We sample that, we get the statistics, the mean and the standard deviation. And then we'll look at a change of 4 standard deviations to say that that's the first arrival. And then we check to see if that's an artificial spike that occurs within the noise, or if indeed this is a signal. So that's worked very well for us. And you know, you saw the results as it pertains to our measure of error.
Yes, yes, yes.
I should mention that we were doing earlier work on the initiation of the crack, and fortunately, there are not a lot of events before peak. We would actually, to get good locations, because the first arrival is key. Velocity is not that critical. It's the first arrival. We would look by human eye. So us and graduate students, undergraduate students would find the first arrival. And, you know, humans are very good in picking out that the characteristics associated with the signal. But we haven't looked deeply into other types of signal analysis. I mentioned at the end, this work, because of the amount of data, is ripe for machine learning. We have worked with, an electrical engineer to make use of signals that are very low amplitude that don't give good locations. You know, so there's still a wealth of information that's there that, for example, I didn't show anything with these other events that we don't locate.
Yeah. Thank you very much.
In the interest of time, I'll just piggyback on that question. I would have asked something similar relating to the first part of your talk, which was, I mean, is the barrier to AE dropping as you see it? And are, machine learning, you just mentioned the one that I was going to ask about, something that previously was really labor intensive and required a lot of human intervention. It seems like we're at a point where that now should be tapering off, but are there other aspects that make this difficult for newcomers to AE to use?
No, I don't think so. So as I said, the software, is written in-house. The system is not that difficult to put together, so we don't have a commercial system. In terms of the machine learning part, we did, work with another group in electrical engineering to make use of these signals that we largely throw out. That is, if we don't get good locations, then, we throw up our hands and we don't use those signals. Whereas there is a lot of information there. So, we have done some work where basically looking at now the characteristics of the entire signal in trying to, let's say, group these together, and then from this group, we call them super AE, because you take 10 or 20 that have similar characteristics, and then you could locate those with smaller error. But we haven't done that. That was maybe 6-7 years ago now, Jim. And what we've been pursuing is trying to understand why we get all this shear, why we got these alpha values that are shear dominant little cracks, when everyone always talks about tensile cracking, right? So.
Right. Well, terrific. I don't want to keep you too long, and I'm sorry for the shambles there at the end. I'm glad everybody reconnected, but me, like, I got the same message that you all got. Suddenly the host, whoever that was, ended the meeting.
It was supposed to be 50 minutes, so I apologize.
No. So thank you.
The introduction was too long.
No, it's the first time that is happening, so
all the great things you had to say. So, did you guys guess who that faculty member is?
I couldn't see quite clearly enough.
I couldn't see it. I tried
Rich
to
Fino?
look. I couldn't
John.
see.
I thought for sure John would know. Okay.
Oh, I think of Rich Fino, but
No.
Kreisig maybe.
Oh.
I remember Kreisig told me he was a third baseman.
Can you blow that?
In the minor leagues, but he was a pitcher for us. But there are other guys here. Do you guys recognize some of the other people in the first row?
Can you zoom in on it somehow there, or maybe not?
I don't know. Yeah. Oh, I guess I could show you. I could pull up the photo.
Yeah.
Who's on the line here? Is there anyone that you guys won't tell on me, right?
Yeah. No.
Okay. Yeah, I do have it. Let me see. Okay, you see that?
I think you need to unshare and share the thing because I think you shared only the PP, the power.
Okay, hang on. You see that now?
Yeah.
So of course that's Ray.
Yeah, now I see it.
But this guy you might know, that guy you might know, and this guy. This is Dennis Flanagan, so I don't know. Zdenek may remember
I
Dennis
remember him
Flanagan.
very well. Yes, in fact, I talked to him
Student.
about a year ago.
Yeah. So that's me.
What?
Oh.
I had hair though.
Yeah.
Shut up, Jim.
You look like you look like Joe
Ballerini.
Franco.
That's
Ballerini,
Ballerini.
yeah.
Yeah,
And that
I just
guy.
talked to him this week, so.
And John, you know this guy. Another
Smolinski,
Polichko student.
Pat
Yeah,
Smolinski.
Pat Smolinski. Yeah.
Yeah,
Oh.
I was
So-
afraid you'd have a basketball picture and I'd be in it.
I couldn't find, I wrote to Ballerini. He was supposed to send me something. He didn't. So it's the only one I could find.
Oh, it's
Oh,
brilliant.
that's a good one.
Is
Tell
that?
Ray how it looked.
Yeah, I bumped into him yesterday. He has his own news. That
Oh,
I-
you saw him yesterday?
Yeah, I saw him here in the hallway, and yeah,
In
he
the
has-
hallway?
Yeah, yeah. He has his own news to share, which I dare not share on share for him. But yeah,
I
too bad
should
he
send
wasn't-
that to him.
yeah, yeah. If you send it, would you? Could you send it to me? He'd love
Sure.
it.
Yeah, I'll send it to you. Yeah. If you promise not to show anybody else or say that. I guess I could crop it and send it to you.
Don't worry. I'll keep it. Yeah, I'll keep it.
Anyway, it's great seeing all you guys and thank you for the invite. Yeah, I was really nervous, by the way. So I didn't sleep too well last night.
Oh, thank you for
Surprised to see
coming.
Stu, because I didn't have any references for him and his work. So I made sure I had that paper with that nice work that you guys did on the control for that composite material.
Yeah, for the
So
software.
I had to make sure that was there in any case. Yeah.
Thank you, Joe. Thank you so much for
Thank you.
coming.
Thank
Yeah,
you.
virtually.
Stay in touch.
Th-
And
Yeah, thanks,
Thank
Joe.
you.
It's good to
Thank
talk
you,
to you.
Joe. Thank you.
Yeah.
Bye-bye. Bye-bye.
Bye-bye.
Bye-bye.
Yeah.